Now what's the problem with this kind of a circuit implementation, right? So you look at the clock, how many transistors is it driving? Clock and clock bar separately. Yeah, 4 each, right? And so you look at the problem, large clock load, right? At least 4 transistors, right? 1, 2, 3, 4, 4 transistors per clock and clock bar. Now how many flops will you have in your chip? You're going to have a huge number of them, right? In a million gates, you could have, if you have a billion transistors, you could have something like 500,000 flops. Because ultimately, in order to probe a digital system for digital testability, you will put what is known as a scan flop, right? So I will not have time to talk about that, but the scan flops are going to be large in number. That's the only way you can test the internals of your circuit. Because of that, the load is very high, and therefore this is not a great architecture. So we want to get rid of transistors on the clock. Okay. So how do we do that? Now let me just draw only a latch. Okay, here. Let me see that. Oh, great. Here. Okay, this is the latch. So this I can first of all redraw little bit for some, just to get a better understanding. This is my D. I am going to call this as clock bar, right? And the output here is going to go through an inverter, right? And clock bar, and so wait. So this is, makes sense? Topologically the same thing, right? This is my QM. Okay. Now, in order to get rid of this, load, what do I do? Technically, I can remove this. I know it has some problems, but we'll come to that. Okay. Obviously, I'll get rid of the PMOS transistor because that is going to be larger in general. I'll only, instead of a transmission gate, I will use an NMOS pass transistor in order to make this latch. Clearly, this has obvious problems. In the sense, I cannot pass a 1, right? But passing a 1 is not that bad, because now remember there is the feedback path, right? So as long as the capacitor can be charged above the trip point of this inverter. Okay, what are the inverters, by the way? I had one more inverter here, right? Sorry. D. This is I1, this is I2, and this is I3. Okay, as long as this node here, node X, can be charged above the trip point of I2, there is no problem, right? Because then the feedback path will take care of keeping that value, right? Discharging to 0 is never a problem. NMOS can discharge all the way to 0. So there is no issue here, right? But of course, remember that when you are trying to charge using an NMOS transistor, charge to a capacitor to VDD, it's not just the fact that it can go only up to VDD minus VT. It starts charging slower and slower as the capacitor charges. Why? Because VGS is the source, is actually the capacitor node. which is charging up. Therefore, VGS keeps dropping with time, which means it's an asymptotic process. It will take forever. It's a very slow process, right? Therefore, you can do one more thing, right? Namely, get rid of this transistor and put it as a PMOS transistor back here. Okay, you can do that. Fine. So let me draw that separately here. D, QM, I1, I2, I3, and now there's only one transmission gate, PG1. Okay. So the difference between these two topologies or configurations is that in the feedback path, right, I have removed that multiplexer select line, right. So now I can ask you a question. Do the sizes of these transistors matter, of let's say I2 and I3 matter in order for the flop to function correctly? Sizes of I2 and I3 transistors, do they matter in order for my transistor, flop to function correctly? Forget about timing. Setup time can be large, bad, I don't care. Functionality wise, in the sense, if I want to sample data, I should be able to flip a node. I should be able to flip QM, right? That's what writing means. You're flipping the data. Can I do that? Unconditionally, irrespective of the sizes in both cases. Okay, so let us look at what happens. Suppose I want to write data into this configuration. I'll call this configuration C1. This is C2. Okay, I want to write data into C1. My assumption is what? My assumption is very simple. I'm going to assume that clock and clock bar are instantaneous. Clock bar, instantaneous, no skew. So the moment I want to write data into X, my clock goes high, clock bar goes low, thereby turning off this path. Right? It's cutting off that path. And it is going to turn on this guy. Correct? So where am I? What is happening when the clock was 0 here and clock bar was 1? Exactly the opposite happens, right? This is on and this is off. So node X is being driven by how many gates? I1, and through that transmission pass transistor, NMOS transistor, right? This is the only path which is driving node X. Therefore, sizes of I2 and I3 do not matter. I can make them unit size inverters and still it will function correctly. Delay may be bad. Okay. Now consider case the configuration C2. When my clock is low, clock bar is high, right? So where is this? I need to label it correctly, right? So this is clock bar, clock, and this is my node X. Now when the latch is transparent, that is clock is 0, clock bar is 1, how many gates are driving node X? I1 and I3. Clearly, this guy is driving node X and so is this. Right? So let's say that this node x is equal to 0 and I am trying to write a 1. How is that node going down to 0? Huh? So what I'm saying is, consider this case where my clock is 0 so what I'm saying is, consider this case. Latch is now opaque. Data has stabilized to some value. I want to write a 1. D has become 1, right? So therefore my D has become 1 like this. What was the initial value inside for QM to be, I mean, if D was, if the internal node was X was 0, right? That means this guy earlier was 1, correct? 0, 1, and I'm trying to flip that data. Okay, so therefore, sorry, my data has to fall. Yeah, that's what I was getting confused with. Okay, internal node is 0 when the clock was high, when the latch was opaque. Now the latch is going to become transparent and I want to flip that data, right? That means my data has to fall so that node X has to go high, correct? So when the latch was opaque, node X was being driven by which gate? I3. So in order for that X to be 0, there was a pull down transistor of I3 which was bringing it down to 0, correct? Now when the clock now goes low, right, and the latch becomes transparent, how many gates are driving node X? I3 and I1, but I1 is now driving it high because data has gone low, correct? So therefore this guy is going to drive it through a PMOS transistor like this, high. Which amongst these two should win now? I1 should win because I want the data to flip. That means the PMOS transistor should be stronger than my pull down NMOS transistor in I3, right? That's why if you see, I would have deliberately drawn this inverter a little smaller in size. Okay, so you need this in order to get the functionality right. And as is very evident, this style of latch is basically classified as breaking feedback path, and this is not breaking it. Not breaking feedback path. Okay. The issue with the latches not breaking feedback path is, you might design it, you might choose a width such that the PMOS transistor, right? And by the way, this holds even for the other polarity. If node X has a 1 and I want to flip it to 0, then the NMOS of I1 should be stronger than the PMOS of I3. It has to hold both ways. So in general, I1 should be much stronger than I3. So you design it with some widths and make sure that it is stronger, right? But you can ensure this only under some process conditions. Now when you manufacture it and across a million dies that you manufacture, it may so happen that in one of those chips, it just so happens that, let's say, the VT of I3 drops significantly and the VT of I1 goes up significantly, due to random variations. In that case, it could happen that this flop may fail because you will not be able to flip that data. That stronger assumption breaks now. So if you want to be absolutely sure, then you have to do this breaking feedback configuration. But of course, that has a problem of you need more transistors. Okay. But otherwise, if you are sure that I have, you can size it up, you can throw in more transistors, give enough area and all that, then there is no problem. You can even use the by not breaking the feedback path, you can manage your flop design. Okay. Just a quick thing to wind up this. So if you look at this feedback path here, let's say this is V in, this is V out. Okay. So if I plot V out versus V in, right, then you get the voltage transfer characteristics of I1, I2, right. This is VTC of I1. Now on the same thing, I have to plot the VTC of I2. What I want to now find out is what are the stable points on this in such a configuration. Where is it that I am guaranteed that the output will be stable always? Okay. So now, which means that there is a relationship between V in and V out because of I1 and V out and V in because of I2, and all of these constraints have to be satisfied simultaneously. Only then it will be stable, right? So, like for example, if I put 3 of them in a feedback path like this, it will keep oscillating. That's a ring oscillator. So therefore, I don't have a stable point at all. Here I am trying to see, because there are 2 of them, it seems like there is a stable point. I am trying to see what the stable points are. Okay. So to analyze that, you plot V out versus V in for I1, which is of course obvious for us. V out is now becoming the input of the other gate, and V in is becoming the output of I2. Therefore, you have to now plot this in this particular way, right? Okay. So what are the stable points? I have to ensure that the combination of V in, V out is consistent across all of them. So clearly V in equal to 0, then this will be VDD. If that is VDD, then this will be 0 for I2. So therefore, that is one stable point, right? Similarly, this guy. If V in equal to VDD, right? If this is VDD, then this will be 0. No problem. The feedback path is perfectly consistent, right? What about this point in between? That also seems to be a correct thing. So for example, if this is VM, let's say the trip point is VM, right? Then the output can also be VM. V in equal to V out equal to VM. That's how we defined it. So if this is VM, output is VM. If that is VM, this is also VM. So is this another stable point? Why? Exactly. If even a small noise comes on this node, right, then what will happen? V in is now shifting by some positive value. Okay. That means what will happen to V out? It will switch to a large what? Will V out reduce or increase? Reduce, because the gain at VM, V in equal to V out equal to VM, is a large negative value. That means V out will come and sort of settle somewhere where? Here it was, if V in increases a little bit, then V out will come somewhere here, right? V out has to drop. So this will fall like this. Now for the, look at the other inverter. V out has dropped, right? So therefore, what will happen to the V in there? The output of that inverter, it will increase. So that means this will go somewhere here, right? So within like 2-3 steps, it will go and settle at VDD. Similarly, on the other side, the noise was negative. Within 2-3 steps, it will go and settle at 0. Therefore, that point is not a stable point of operation. It's known as a point of metastability. Okay, this is a point of metastable point. Basically, the only way to come out of metastability is for noise to come and help you out, right? And that time is actually random. It can take arbitrary amount of time for a flop to come out of metastability. So you have to ensure that the flop also doesn't go in there. Okay, that can be a problem because this time is now random. Okay, so we won't cover too much beyond this in this course. That's a separate topic of study. But you need to know that this can be a problem in flop designs. Okay, point of metastability and how to come out of it. What case will it go to VM? Let's say that I have a node here and I have a tri-state inverter driving this node, 2 tri-state inverters, and both tri-state inverters happen to be switched off for a short while. Then this capacitor value will be somewhere in between. That can come and settle at VM, right? Or you have a floating node. Basically, floating nodes are very dangerous because some capacitive coupling can bump it up and then it will just remain there. Then this guy will go into metastability. That's all. Then the feedback loop will take over. So